Hello and welcome back to Calculus 1 Saturday edition. We are starting chapter 4. We are going to talk about the extreme values called extrema, which is minimum and maximum, or plural minima and maxima when you have a couple of them, and you definitely can have more than one. You can have infinitely many, and we'll see those situations as well. Well, you've seen them already. I don't know if you recognize them. Can you tell me what has infinitely many min and max values? Anyone? Infinitely many minimum values and maximum values.
Is that the cosine and sine function?
Excellent. Perfect. Yeah. Excellent. Sine and cosine functions have infinitely many of those. Perfect. All right, but we are going to start with just a few. So we're going to draw this type of a shape. That's going to be some function f of x. I'm not even going to bother drawing the x and y coordinate system because we don't care at this point in time. And I want to recognize that there is a max value there, a minimum value there, and another maximum value there. What we know from before, what you should know from before, is that you have this horizontal tangency going through these, regardless whether it's a min or a max. And what we know from there is that slope is equal to 0 on all of these tangent lines without any question. So now, what we see here is a maximum that it's lower than the other maximum over here. And we are going to, for these, right, we are going to have different names. So the one on the left will be called relative or local maximum. I don't care which word you use. The one on the other side is called the global or absolute maximum. Let's go absolute, also known as global. Why? Because it's the highest maximum that we have. So which one is this one? Is this relative or absolute minimum then?
That is absolute.
How about this point? Can this one be absolute if there is a lower point, right?
Yeah, you're right. It's continuous.
It's going to be relative. Yes, it's continuous forever. So relative or local min. And the only reason is if you are to extend this tangent line, all of these points and all of these points forever will all have lower y value than your minimum, which is why this minimum cannot be global minimum. If you draw function this way, like x squared, then this one over here is going to be your global absolute, whatever, absolute min. So we have to be careful and differentiate between these two words, right? The word global and the word global and the word local. And please use that common sense, right? In sense that this one over here is the highest point locally, but it's not highest point globally. And the same thing, this is a minimum, which is the lowest point locally, but we can definitely find a point over here that is lower than that one, so it cannot be a global one. So
Professor,
I hope.
I'm sorry. How would you define the maximum on the right side then? Is it both a global? on each side?
You mean here?
Yes.
No max.
No max at all.
No max at all, because this function will go forever up. So we only have one absolute min and no absolute or relative max in that case. Tangent function has nothing. E function has nothing. So if you take a look at good old y equal e to the x, and you look at the graph, you would have this asymptote, and it goes like this: no min, no max, we would say no extrema. The purpose of this lecture is not just to learn about min and max, but also learn how to compute them algebraically, so you don't have to have a graph. That's a big part of this. All right, so we have put some words down, right? And we hopefully understand what is the relative versus absolute, or local versus global, right? Min and max, and when they occur and how they occur. Now, I usually get the question from students, what about sine and cosine function? Are those, for the sine function, are those all global or local max values? They're all global max values, because those are all the highest points. If you have a local max, that immediately implies that there is a point somewhere that it's taller than that value. But the domain, the range of sine and cosine function is from -1 to 1. So there are no points that are taller than 1 and lower than -1. Therefore, those ones are absolute max and absolute min. And you have infinitely many of them. So it's a very interesting situation. Right, so it goes up and down and up and down and up, and this is terrible, but I'm drawing at an angle here because I have to keep the tablet at a particular angle for cooling. And all of these values that you see, they should all be equally spaced, and they should all go up and down to these two squares. They're all ABS max, and they're all ABS min. And this is very valuable for you to memorize and remember, because if you don't know these things, you can get confused. Remember, in order for something to be a relative minimum or a relative maximum, there have to be points somewhere in the domain that are either lower or lower than relative min or higher than relative max. That doesn't happen in our sine situation here. They're always lined up at 1, and you will never find any point higher than 1. So that's why they're all global or absolute max and global or absolute min. All right, and then we have functions like e to the x, 1 over x, ln x, and so on, tangent x. So a whole bunch of functions that do not have min and max at all. So no extrema. So we would like to see how we can figure these things out. And the first thing is, there is the definition of something that is called the critical point, right? And that one will eventually give us the min and max through calculation. So here it is, definition written in blood. This can pop up on the exam as something you need to know. So an interior point C of the domain of F, at which f prime of C is equal to 0, or f prime of C does not exist, is called critical point of F. Is called critical point of that f of x. I'll call it f of x here too. So this is the mathematical definition, and I underline this word or, And I do that because, you know, I teach calculus for years, and I know that unfortunately vast majority of students does not read and learn and study and understand theorems, definitions, and that kind of stuff. And then they completely drop this part, and because of that make mistakes. It's not just when the derivative is equal to 0. It's also where derivative does not exist. You can have your maximum value. So I'm going to first start and, so another part here is critical point turns into minimum, turns into maximum, turns into inflection point. More of that later in a chapter. Later in 4 point whatever the hell it is. I think it's 4.4. I don't know. Later. And then vertical asymptote. Because when the derivative does not exist at the point, it could be a vertical asymptote, right? You can quickly come up with that example. I'm just going to point with a example to the vertical asymptote thing because, again, people say, didn't we learn a limit? Yeah, we learned a limit, but that's all tied in. It's mathematics, so everything ties in together. If your function is f of x equals 1 over x, its derivative f prime of x is what? Negative 1 over x squared, right? So if you are looking at 0, f prime of 0 does not exist because you would get negative 1 divided by 0. That's no bueno. But we know that this particular function at 0 has a vertical asymptote because it looks like this, right? Opens, goes down like that. So it could be a vertical asymptote at that point. So today we're only discussing these two parts, min and max. But in the back of your head, we're going to upgrade that. And also in some cases, right, you're going to get a false positive, right, which is, oh, it turned out it's actually a vertical asymptote. So we have to be careful about all of these things and then go from there. All right, so let's work this out on the cheapest problem in the galaxy. Y equals x squared. So y equals x squared is, we know what we're supposed to do. Find the derivative, which is 2x, and we set that equal to 0. Remember how I said in chapter 4, it's not just differentiating, but you also have to set it equal to 0 and come up? Yes, because now this equation will tell you that the critical point is at x equals 0. When you solve that equation, you get x equals 0, get y, which is y is equal to 0 squared, which is 0. You have your critical point at 0, 0. Do you? Yeah, you do, right? You know what the x squared looks like. You know that at 0, 0 there is a minimum. And this calculation we just did tells us that there is something at 0, 0. What is there at something? What is that something? Is it a minimum? Is it a maximum? Is it this inflection point? Is it a vertical asymptote? Right? This calculation here tells you there is something there. It's a critical point. Now, what is the type of the critical point? Like, which point? What are you talking about, right? So now you have to go in and you have to say, all right, so this is my critical point. It's minimum or it's maximum, and we are going to have more of these things later on to try and figure out what is the actual, where it's a min or a max. For now, we can only figure out what is it by a very painful technique of computing points around it. Look, when you have a minimum, so this is your critical point right here. If you go a little bit to the left and a little bit to the right, you see that the y values that you get are higher than the y value of your minimum. So these two are test points. And if their y values are larger than the y value of your critical point, yc, then the point is a minimum, because these points are taller. For a maximum, common sense, again, here I have my two test points, and I have critical point. Y smaller than yc, that means that the point is a maximum. So now, since I know my critical point is this, I can just quickly pick test points. Again, we don't have to do this for x squared because we know the graph. But what is ln x squared minus 1? Like, do you know what the graph for this is? Of course you don't, right? I mean, we're going to learn how to graph this by hand in 4.4, I believe, or whatever. But the fact is that the graph is not readily available to you, but the derivative calculation is. So now when I pick test points, right, I can pick a test point of -1 and another test point of +1. You can do 0.1 to be closer, 0.0001 to be closer. But I'm just going to pick these two values. And when I plug them in original function, I get 1 squared is 1, 1 squared is 1. So what are my points? My points are -1, 1. 0, 0 is my point in question. And on the other side, 1, 1. What I see here is that this y value is higher than 0. I want to write 1 bigger than 0, thank you. And this one over here is also 1 bigger than 0. Because these endpoints are higher than the point in the middle, this must be a minimum, because there are two higher points on the sides. The y values are taller. So it's a very simple thing. It's annoying to compute. We'll see later how you can avoid that computation and quickly tell which one is it. We need for that second derivative test, which is not the part of this lecture. So now you know. Remember how I told you that y equal e to the x has no min or max? I know you know the graph. I know you see it on the graph. But again, you can do calculation. F prime of x is itself e to the x. And when you set that equal to 0, there is no solution. And if there is no solution, no critical points. And when there are no critical points, there are no min-max. That's a logical procedure there, right? So if the IQ is bigger than 7, then you just follow the steps. You have your y equal e to the x. You have your derivative. You set that derivative equal to 0 because you want to have the horizontal tangency. This 0 here is not arbitrary 0. This 0 is that m equals 0 business. You are looking for x values that are making the slope of the tangent line to be 0. That's why you are setting everything equal to 0. You're not setting it because the theorem said so. You are setting it because the concept of that the derivative of the tangent, the derivative of the function gives you the opportunity to calculate slope of the tangent line, because that's what the m is, right? M was the first derivative computed at whatever value. So if you are setting that to 0, you are looking for the slope to be 0, horizontal tangency. All right, cool. So again, the derivative of the function is this. When you set it equal to 0, use your pre-calculus. There is no solution for this equation because e to the x does not cut through x-axis to create a 0. Therefore, there is no solution. That means no critical points. And if there are no critical points, that means no min, no max. All right. Careful. There is a careful problem. Y equal x cubed. I know it's not a part of this lecture to talk about the inflection points, but it's better just to be aware that you don't have the whole picture yet. So, don't get too relaxed, right? We all know what happens to a fighter or a boxer or whatever, goes into a ring and gets relaxed and puts the guard down, right? Gets smacked in the face. So the same thing with this. You do not have all of the pieces of the puzzle yet. So you have to understand that having a having a solution for equation equal to 0, derivative equal to 0, doesn't guarantee min and max. And this is the perfect example for something like that. What you have here is the derivative f prime is going to be 3x squared. And when you set that equal to 0, divide both sides by 3, take a root of both sides, you get x equals 0. And then you go and you ask yourself, is this a min or a max? And you quickly find that it's neither, right? Because remember, what is the tool that you have? Your tool is to pick, point to the left and point to the right, and see if both of those points are above or both of those points are below. But when you make these two choices, -1 cubed is -1 and +1 cubed is 1. See, one is lower, one is higher. Well, that's not going to be a min or max. And you can see that also on a graph. You know what the x cubed looks like. Looks like the tangent graph, right? So here is your -1, 1. Here is your +1, 1. When it goes through the origin, which, right, is the critical point in this case, it's not a critical point in terms of min and max. It's going to be that inflection point for later in chapter 4. I believe it's 4.4, or maybe 4.3 or 4.4. So you're going to learn that. It's not a big deal. But you need to know now that not every derivative immediately leads you into, derivative equal to 0 immediately leads you into -1 and +1. So this is my introductory story of min and max, and now we just need to practice a few more examples with a bit more complicated functions. This is, guys, literally 3 pages in your textbook to explain. It's a very short concept. It ties into that story from chapter 3, when we said that every time if you want to sketch the derivative function, every time when the derivative crosses the x-axis, you have a min or a max. That all ties obviously into this. All right, so let's take a look at a few of these, ones that have ln's and product rule and quotient rule and all of those good things. Let's go with, okay, let's start with problem 35, because it is 1 over x plus ln x. One important thing about you working these derivatives and things around is to make sure that you know that some points are already vertical asymptotes, and then there are certain parts of the domain. The domain of the function is set, so part of the number line might be not even considered in the calculations. So what is my domain in this case? Well, domain of 1 over x is -infinity to 0 united with 0 to infinity. Because it has a vertical asymptote at 0, we have to break it there. But then the ln is just 0 to infinity. And that's the restrictive one, which means that the entire domain is 0 to infinity. If I compute any numbers outside of this, we just disregard them. Okay? Because those numbers are not in the domain. Now, how did I combine these two domains? Well, if you know each domain separately, then we can use common sense, right? If I can pick from this set here, if I can pick -2, and I can't plug that in ln because it gives me complex numbers, clearly -2 is not in the domain for everything, right? It is just working for half of the equation. But if you use a +2 or 3 or whatever from the other side, that works in both of these. Therefore, that is okay to pick. So that's how we eliminate this, because of the ln. ln is the one that it's a limiting function in this case to be very, to pick the numbers for your calculation. So now we know that domain is 0 to infinity. Again, this domain and range stuff will be back in a later section as well. Now, let's find the derivative. Well, that's easy. Derivative of 1 over x is -1 over x squared. We said that. And plus, the derivative of ln x is 1 over x. Ooh. We just created a matter out of nowhere, huh? You see that this domain is actually -infinity to 0, union 0 to infinity. Because this function graph says this. It has both positive and negative side. This function graph says this. Right? So when I set this second equation equal to 0, it could possibly generate numbers that are in here, but because they are not in the original domain, they will not be considered as min and max, because as far as the original function is concerned, those points don't exist. The derivative might spit them out, but we have to disregard them. This is the reason why knowing the domain and range and being mentally present when you do these problems is very important. So let's go. -1 over x squared. Well, let's just write this as 1 over x minus 1 over x squared equals 0, when we set it equal to 0. And the way you solve this is, should I say clearly, move 1 over x squared to the other side. Then you can cross multiply, get x squared equals x. And now, to solve this, please don't divide by x. I mean, in this particular case we can, but in some cases you're going to lose solutions. So don't. Move x to the left-hand side, factor x, and look what you got. X equals 0, x equals 1. What do we know about x equals 0?
It's a critical point.
It's not in the domain.
It's not in the domain. It's a critical point. Both of those are correct, and I'm looking for one more concept to seal the deal. What's happening at x equals 0?
It's not on the graph. It's not like graphed. No limit.
Okay. Yeah, it's not a part of the function, but it is something very important there at x equals 0. If I draw ln graph, if I draw 1 over x, if I draw 1 over x squared.
Vertical asymptote.
Yes!
Yeah.
Nice. That's a VA. And here you see how the critical point spit out the value where the vertical asymptote is. And that was the part where, the derivative actually doesn't exist there. but that's where the vertical asymptote is. Not a min, not a max. And you can see that x equals to 0. If you go to the derivative function, you can't plug in zeros here, right? It's not in a domain. It is exactly the vertical asymptote that interrupts the domain. So that's a very important thing. Now also, it spit out x equals to 1. So we are expecting to have some min or a max value at x equals to 1. Do we? Hope we do, right? So this one is my critical point. And now I can take that critical point and find its y value. So I'm going to find the function at this critical point. The function is given as 1 plus, what happened? Thought someone said something. Okay, y equal.
I'm sorry, I unmuted my mic for a second, but didn't the definition for critical point say at function does not exist? So you said that 1 was your was your critical point, but wouldn't 0 also be a critical point?
It is.
Okay.
Yes.
If you scroll down, it looked like you're only pointing to the 1 that was the critical point.
Well, this is a critical point which will turn into a min or a max. This is a critical point which turned out to be a vertical asymptote.
Okay.
There's no y on that.
Very good. No y value. That's an amazing observation as well, because the critical point, as you can see, right, we obtained the y value, so critical point, and now I want to know, is it a min? Is it a max? Is it this other thing that we haven't learned yet, right? The inflection point. So what is it? And that I'm going to simply just use my chart of values here, because that's the tool that I have so far. And use 0.9, use 1.1. Obviously, you're not going to use 0 and 2 because you can't compute 0. But it's okay to use 0.9 and 1.1 and then see if they both go down, it's a max. If they both go up, it's a min. If one is up, one is down, it's an inflection point. It's a very simple thing. Again, annoying to compute, but such is life. So go to the original problem and compute 0.9. So you have 1 divided by 0.9 plus ln of 0.9. And I got 1.00006. And now we do the same thing. 1 divided by 1.1 plus ln of 1.1. And that gives me 1.004. They are both higher than 1. And that means that this is a minimum, because I have this situation, right? That's my 1.006. This one is a little bit lower, 1.004, and this one over here is just exactly 1. These are all y values, right? So the two numbers that we computed are higher than the critical point, so it's a minimum. So we would say minimum at 1, 1. Now we don't have the whole picture yet for the whole, so I can't really go in detail whether it's a global or local or any of that kind of stuff, because it's a problem. Okay. Oh, you know what we can do? How about we take a look at the graph? Let's ask Desmos to give us the graph for this and verify that 1, 1 has some kind of minimum, and then also there is a vertical asymptote at 0, right, that the function follows. Because the function is at the end 1 plus ln x, right? And we should not have a line for that function to the left of the y-axis, because we said that our domain is 0 to infinity. All right, so let's jump into Desmos. Oh, I have to share screen for Zoom. Where's Desmos? Right there. And our function here is, I believe, 1 over x plus ln x, yes. So 1 divided by x plus ln x. We already see everything. There is no line to the left of the y-axis, and you can see clearly 1, 1 has a minimum because the function goes up from that point on. So it's very easy to verify that you are doing these problems correctly. I mean, if you calculated that there is a max at 2, 3, and your graph is showing the minimum at -7.5, clearly something is wrong. You either calculated it wrong or you typed in the formula, the graphing, right, equation wrong. Something has to be wrong. So please, be careful about that. All right, let's go back to another example of this. What else do they have that looks spicy? I mean, they have a lot of cool stuff here.
Hey, Professor.
Yes.
Just a quick question. Earlier you mentioned that the theorem that you wrote out prior was could have been a potential question on the exam. That was in reference to the third exam, right?
Yes.
Okay, just making sure.
We are now in the third exam material, exactly. And
cool.
you still need to tell me the weekend for exam 2, because now we are ready for exam 2. All right, one more problem, and then after that, one more quick concept, and we're done. So sine x times cosine x, right? There is that. So now we know what we must do. We must set this equal to, well, we must find the derivative set equal to 0, and then solve whatever we get from there. Now, what's the derivative of this? Like what rule I'm using? What's going on?
There's a product.
Beautiful. And that's going to give us some kind of mess going in on the other end, right? If you do the product rule here, that's obvious. Copy the first, derivative of the second, plus copy the second, derivative of the first. What you get is the f prime is equal to cosine squared x minus sine squared x. Okay, equal to 0. So now, here's the trouble. How do we solve this? So many of you would say, well, can we move sine to the other side? Can we divide? We get the cotangent and cotangent squared. Yes, all of that stuff works. All of that stuff works. I want to solve this problem in 4 different ways. As long as you know one of them, that's fine. This is the hard way of solving the problem. Especially if you go and now, because you don't know identities in trig, you go and try to force the solution out of here. Then we're going to go and do the joke way. But look at this first. If you go and you say cosine squared x equals sine squared x, then you divide, you already lost solutions. It's never good to divide, right? Because if you are to divide now to get the tangent squared, right, divide both sides by cosine squared x, what you just did is you discriminated against cosine, and you said that that can never be 0. But cosine of pi over 2 is 0. And you just took out all of those. So if you do have any pi over 2 solutions, dividing both sides by cosine squared killed all of those solutions. You're not going to see them. You're never going to see them. And then you might get everything wrong. Then you graph it and you say, well, I see the solutions at pi over 2. Why is this wrong? And all of that stuff, right? Well, never divide. So what is the way to solve this thing? Well, if you know the trig identity for this, the problem turns into a joke. Cosine 2x equals 0. Ooh, right? So now, where is my cosine? 0. It's 0 at pi over 2, and it's 0 at 3 pi over 2. So, 2x is equal to pi over 2, and 2x is equal to 3 pi over 2. The first one is x equals pi over 4, and the second one is x equals 3 pi over 4. And now I have these two. Now, I did not specify, the book did not specify any of those domains, you know, from 0 to 2 pi or anything like that, which means that they want all min max values here. And because of these two, you see that your wave is twice as fast as usual. So the period is pi. So you can quickly come up with x equals pi over 4 plus n pi, and x equals 3 pi over 4 plus n pi, to have all of the infinity of critical points. So these are all critical points that the function has, going from negative infinity to positive infinity. That's infinitely many. Now, which one is a min? Which one is a max of these, right? You can compute that by moving a little bit to the left, a little bit to the right, right? So you can use, when you have a pi over 4, it's squeezed in with pi over 6 and pi over 3. You can use these two to figure out the y values, whether they're higher or lower. So that was one way to go about this. I already told you the other way, which would be to divide in the cosine. But is there a boss way? And when I say a boss way, I mean a boss way. Right? The one where you put the sunglasses on when you're done with the problem and just walk out. Purple. Use the identity to write this as 1/2 sine 2x. Because sine 2x is 2 times sine times cosine. That's what it is. So in that case, 1/2 sine 2x is that half is needed, right? Because you would multiply here out of nowhere. You need to get rid of it. So it's going to be a half that cancels it in. I mean, if you know identity, sine 2x equals 2 sine x cosine x, it's a no-brainer that these two goes on the other side as a half, and then you just have sine times cosine. Now, obviously, that's something that stays with you if you practice these problems because they're fun for identities. So now when you take the derivative, f prime of x, derivative of sine is cosine, so you have 1/2 cosine 2x, and then the chain rule spits out 2 that kills a half. There it is right there, except you did it in one step. right? And you had no product rule and a whole bunch of stuff. Now, obviously, it assumes the knowledge of things that you have seen before. And if you truly learned them, then you can just use them and cut out a lot of work and a lot of frustration. So that will be the boss way to solve this. Okay, what is left? Well, min and max on the closed interval. So far, you were looking for min and max on the entire domain. And we have seen functions that do not have min and max. 1 over x, 1 over x squared, e to the x, ln x. Right? None of them have min and max. But if you take a look at the square root of x, there is something very interesting happening there. It does have a global min, but it's a weird one. If you take a look at f of x equals square root of x, your domain includes 0 going to infinity. So when you have this, and then it goes wee like that. ABS min. But it was on the closed interval. Closed interval meaning endpoints of the interval are included. Let's write that in blood. Endpoints of the interval are included. A to B. As opposed to what we had before, 0 to infinity, right? Parentheses do not include endpoints. But now, with the closed interval, that means you are including the endpoints. And hopefully, this should be common sense instantly to you. If you have this included, then you always have to have min and max, no matter what function you put up. Because you are chopping up that function and you are using those endpoints. If nothing else in the whole interval is a min and max, then those endpoints are. So how's my y equal e to the x on 0 to 3 doing? All of a sudden I have a min and max. So e to the x on negative infinity to positive infinity, no min max. There's nothing. We have seen that a couple of times. We've seen it on a graph, and we've seen it through calculation. But if I have this function just from x equals 0 to x equals 3, it's this piece. Whee! And stops. And because it's that, here is your ABS min, and here is your ABS max on a function that originally had none of that stuff. Right? It had none of that stuff because when you go to infinity, you never reach a point to stop and claim that's my max. Right? And the same thing here. It always goes closer and closer and closer to the x-axis. Goes closer and closer to 0, but it never becomes 0, so you can claim a minimum at 0. So when you are on the open interval, you can find functions that do not have min and max. When you are on the closed interval, you are immediately guaranteeing you have the min and max, because if they don't happen in the function somewhere in the middle, they will happen at the endpoints. So now, if I go back and revisit my graph from the first, I wanted to curve back. Ah, it's so terrible. There we go. And what I'm going to do is I'm going to put this there, put this there, put this there, and put this there. Your ABS max is still in the same spot, but now this is ABS min. It's ABS min because the function stopped. It doesn't go forever anymore. So this is the lowest y elevation for anywhere in the function. This is the highest y elevation for anywhere, and that's why they're absolute max. Everything else, relative min, relative min, relative max, right? All others. And I can fix this oh so quickly. Whee! Now this is your ABS min, because that's the lowest case, and it's an endpoint now. Endpoint at A, and the other point over there is B. You still have your absolute max the same spot, relative max the same spot, and now this is back to being relative min over here. And this is another relative min. So you can't memorize all of these things and all of these examples, because I'm just going to come up with another picture. You need to categorize this and say, okay, whatever point has the highest y value, that point, that exact point is my absolute max. Whichever point has the lowest y value, that's my absolute min. So now, how does this change the problem? Well, it just introduces calculation of y values on your endpoints. And then when you have your critical points and your endpoints, the highest of all y values is a max, absolute max, and the lowest value of all y values is going to be absolute min. And sometimes those are in the middle of the function, sometimes they're at the endpoints, which is why you always have to compute endpoints if you are on a closed domain. Right, making sure that they have a y value defined there. So let's take a look at homework exercise from the textbook regarding this. Now they give you problems 43 through 68. Right, it's a lot of problems for you to practice this stuff. I'm just going to pick again something that looks weird. You can deal with polynomials and factoring and whatever nonsense. For us, let's take a look at 65 looks amazing. We have f of x is equal to x squared e to the negative x on negative 1 to 5 closed interval. Now the students immediately go into derivative and start, calculating things. I would just say, you know what, calculate the endpoints first. Just so you don't forget later. Because right now you see a problem and you see your closed interval right there. So why not just quickly get those y values? So for x is equal to negative 1, your y is f of negative 1, which is negative 1 squared e to the negative 1 becomes e. That's all it is, e. That's about 2.7, 2.8, whatever. So you have the point negative 1e. And then you immediately calculate the same thing for x equals 5. Y value is f of 5, which is 5 squared e to the negative 5. So that's 25 over e. So over here we have 5 and 25 over e. What is the relation between these two? We only look at the y values. Well, 25 divided by about 3, right, is like 24 divided by 3, which is about 8, right? And this is about 2.78. So that's like almost 3. And this one is about 8, and this one is about 3. So clearly this one is winning now to become absolute max. But we haven't done anything yet in the middle, so it's time for our product rule derivative, copy the first function, derivative of the second function, plus copy the second function, derivative of the first function. Guys, we'll be setting this equal to 0. Factor everything you can. So f prime of x is, I can kick out an x, I can kick out e to the negative x, and what's left is I'll list 2x first. No, I kicked out an x. So I'll list this term first, and then minus x. So now, when you have the factored form and you set it equal to 0, x equals 0, e to the negative x equals 0, and 2 minus x equals 0. And they spit values. X equals 0, that's done. This one has no solution. That's basic pre-calculus, right? Because e to the negative x never crosses x-axis. It asymptotically gets closer, but it never crosses to create a root, so no solution. And then x equals to 2. So I just found 2 critical points, 0 and x, and they fit right in here, right? X equals 0 and x equals to 2. I need to find their y values as well. So for x equals 0, I need a y value, which is f of 0, but that's 0 squared times e to the 0. That's just a big fat 0. So now I have a 0, 0 point, and look, that one is already winning for a minimum. Both of these are positive numbers. One was about 3 in value, the other one is about 8 in value. I don't care exactly to the 16th decimal what they are. It's good enough because 3 and 8 are both bigger than 0. So I don't really care if it's 7.9 or 8.334, whatever. It's about 8. And now I have x equals to 2 to compute, which is f of 2. That's 2 squared times e to the negative 2. And that is going to work out to be 4 over e squared. Now 4 over e squared is going to be a positive number still. So 2, 4 over e squared. I immediately know this is my ABS min because 0 is the smallest y value. And then again, e squared, that's squaring let's say 2.8 squared. That's almost 3 squared. That's a 9. 4 divided by 9, roughly speaking, is a half. So definitely, I mean, you can punch it in a calculator if you don't like this rounding and stuff, but we have a winner for a max. It's the one with the highest y value is the max. And then we have the ones in between, right? The negative 1 point and the 2, x equals 2 point. So those are the in-between values. So anytime when you get a closed domain, right, a closed interval, you have to check those endpoints as well. Guys, this will be back in Calc 3, but it will be back with vengeance. So you need to make sure that the basic concept is well understood if you want to do this thing in a 3D environment later on. So when you have an open interval, then you just work with the derivatives. And when you have the closed interval, in addition to working with the derivative the same way like before, you also have to compute the endpoint y values to make sure that those endpoints are counted if they need to become, to calculate min and max in the essence. And since we don't have the tool, yes, you have to be annoyed by computing one value to the left and one value to the right. And that's that. So I hope you guys are not disappointed with min and max. That's all it is. So figure out the critical point, and then you can use the test points to find out whether your critical point is min, max, or that inflection point. Asymptotes, you should know from before that they are preserved between the function and the derivative. So if the original function has a vertical asymptote somewhere, then the derivative will have the asymptote at the same place. So if you can spot the asymptote in the original function, you know that when that point comes up as your critical point, you know it's a vertical asymptote there already, which is what we had here, not here, in that previous example, right, where I said, there it is, right? We did the calculation and then it gave us x equals 0, but we know that we have a vertical asymptote there, so we're good to go. That's it. We lived. We lived through first section of chapter 4. Next week we are going into 4.2 now. Let's talk about the exam. Oh, let me first say bye to the YouTube, and then those of you on Zoom, pick the dates